Dian, please start when you're ready.
Hello, everyone. Today I'm going to present a paper published in NIPS 21, and the title is No Fear of Heterogeneity, Classifier Calibration for Federated Learning with Non-IID Data. And here is outline. Firstly, I'm going to give you the backgrounds of the federated learning training with non-IID dataset. Next is an observation found in this paper. They found that the problem caused by data heterogeneity is in the classifier. And then they propose a method to calibrate the classifier, where they use the virtual representations in their method. Finally, I will conclude this paper with the performance evaluation part. We all know that federated learning has emerged as an efficient paradigm to collaboratively train a shared machine learning model among multiple clients without directly accessing their private data. And a critical challenge in federated learning is training with non-IID dataset. Due to the diverse user behaviors, a large heterogeneity may be present in different clients' local data, which has been found to result in unstable and slow convergence and cause suboptimal or even degrade the model performance. In the literature, there have been plenty of works exploring promising solutions to federated learning with non-IID dataset, and they can be roughly divided into 4 categories. The first one is client drift mitigation. In their methods, they can modify the local objectives to make it consistent with a global model. Some popular methods like adding a regularization term can be classified to this category. The second one is the advanced aggregation scheme. And in this category, we can apply the weighted sum operation as a server or select the participants with some strategies. So we can improve the model fusion mechanism as a server. This is the second category. The third category is data sharing. We can introduce another small or public data set to help construct a balanced distribution. The last one is a personalized federated learning. If we cannot find a global model to satisfy all clients, and then we can train personalized models for individual clients. And the existing algorithms are still unable to achieve good performance and could be no better than vanilla federated average in some situations. So in this paper, to identify the reasons behind this, they first perform an experimental investigation on each layer of a deep neural network, and they measure the layer-wise similarity among local models and find that the classifier has the lowest feature similarity. And motivated by the above discovery, they confirm that the classifiers tends to be biased to certain classes. So they conduct several empirical trials to debias the classifier by some regularization or calibration methods. And based on the above findings and considerations, they propose a novel privacy-preserving approach called classifier calibration with virtual representations to calibrate the classifier. So these 3 points are the contributions in this paper. Next, let's move to the second part. They have some observations in this part, and they found that the bias existed in the classifier. Let's look at the problem setup firstly. They consider an image classification problem in federated learning. So there are the number of K clients and the number of C classes in that federated learning problem. Given a data sample, the model can be divided into 2 parts. One is a feature extractor, and the other one is a classifier. And the classifier is the last layer of the model. So the input of the feature extractor is the image or data itself, and the output of the feature extractor is a feature vector. And the input of the classifier is that feature vector a feature vector, and the output of the classifier is a probability distribution. And for each client, the goal is to minimize the local loss function with current global model and its own data set. And for the server, it will average all local models and generate a global model. To understand how non-IID data affect the classification model in federated learning, they perform an experimental study on heterogeneous data set. Let's see their experimental setup. They use a CNN model with 7 layers to train the CIFAR10 dataset, and the non-IID settings are obtained from the Dirichlet distribution. The main idea of their experiment is to take the similarity measurement. They leverage the CKA matrix to measure the similarity of the output features for each layer. And the CKA is a similarity metric. It can measure the similarities of a higher dimension rather than measure the similarity between the paired data points. So the similarity score is between 0 and 1. 0 means not similar at all, and 1 means all the output features are identical. And in their experiments, they use the federated average algorithm, where they take 100 communication rounds, and for each round, they take 10 local epochs. And next, let's see their simulation results on similarity between output features for different layers. And interestingly, we can find that the features outputted by the deep layers show the lower similarity. For example, the similarity of the last layer of the classifier is smaller than the similarity of the first layer. It indicates that for federated learning models trained on non-IID dataset, the deeper layers have heavier heterogeneity across different clients. And by averaging the pairwise CKA similarity in figure 1, we can obtain a single value to approximate the similarity of the feature output as shown in figure 2. We can calculate the average similarity for each layer. And the result shows that the models trained on a non-IID dataset, this orange line have this yellow line have consistently lower feature similarities across clients for all layers compared with the similarity trained on this IID data, the orange line. And the primary findings is that for non-IID training, the classifier shows the lowest feature similarity among all layers. So that's the first observation of their experiment. Next, let's move to the second observation. To perform a deeper analysis on the classifier trained on non-IID data, they illustrate the L2 norm of the local classifier weight vectors as shown in figure 3. The first figure is the label distribution of the non-IID dataset, and the second and the third figure are the weight norm in different rounds for non-IID dataset. And the fourth figure is the weight norm in 100 rounds for IID data settings. And from these figures, we can observe that the classifier weight norms would be biased to the class with more training samples at the initial stage. For example, the client 8 has many data points on class 4. So the corresponding weight, the corresponding weight L2 norm in the is large at the initial training stage, which refers to the bias. But at the end of the training, models trained on non-IID dataset suffer from a much heavier biased classifier than the models trained on IID dataset. This means that the weight norm is not identical among clients and classes in the non-IID data setting. So that's their second observation, which means that the non-ID data set leads to the heavier biased classifier. Based on the observations of the classifier, they have a hypothesis is that because the classifier is the closest layer to the local label distribution, so it can be easily biased to the heterogeneous local data reflected by the low feature similarities among different local classifiers and the biased weight norms. So that's their hypothesis. Based on the hypothesis and the observations shown in the last page, they believe that the bias in the classifier is promising to directly improve the classification performance. Therefore, they empirically propose 3 methods to debias the classifier. The first one is a classifier weight L2 normalization. They can normalize the weight of the classifier. In particular, the classifier is a linear transformation followed by a normalization and a softmax. The second method is a classifier quadratic regularization. In this method, this means they add a regularization term on the local loss function, but we should notice that they only restrict the classifier weights, not the whole model parameters. And the third method is classifier post-calibration with IID samples. In this method, they fix the feature extractor and calibrate the classifier by the IID data samples. And for the third method, it is just an empirical study. It is not practical since we need the features of all IID data samples. It is not practical. And this table shows their simulation results. And from this table, alpha is the non-ID level. From this table, we can observe that regularizing the L2 norm, the class norm method, this method is consistently effective, but with special minor improvements. This method, for this L2 norm, the class norm method, it can only effective in light data heterogeneity, but would have less help or even lead to damages along with the increase of the data heterogeneity. And for this regularization, the classifier parameter methods, this class prox methods, it is consistently effective, but with only the minor improvements. And surprisingly, we found that calibrating the classifier of the federated average model with all training data samples brings a significantly performance improvement for all degrees of data heterogeneity. And to further understand the classifier calibration techniques, they additionally perform calibrations with different number of data samples. And the results is shown in this figure. And we observe that the database classifier calibration performs consistently well, even with a smaller number of training data samples. And so this significantly improvements after adjusting the classifier strongly verify their aforementioned hypothesis, that is, the bias is in the classifier. Therefore,
could you go back to previous page, please? The calibration here means
this means yeah, this means we fix the feature extractor and we use the IID data samples to retrain the classifier. Then we call it, we can calibrate the classifier.
Okay. Yeah, I just want to get the definition. Okay.
Yes. Okay, so let's move to Then I will introduce the calibration methods proposed in this paper called classifier calibration with virtual representations. The proposed CCVR runs on the global model as a server after the training. So it is a post-processing method. The main idea of the CCVR is it uses the virtual features drawn from an estimated Gaussian mixture model to calibrate the classifier without accessing any real images. Let's recall their problem setup. The model can be divided into two parts. One is the feature extractor, and the other one is the classifier. So we can summarize the flow path of the CCVR method. The first step is feature distribution estimation. We use the feature extractor to extract the features of each client and each class. And then we can estimate the feature distribution based on the obtained features. That's the first step. And the second step is a virtual representation generation. Based on these estimated distributions, we can generate some virtual representations of the feature. The third step is classifier retrain. We can use these virtual representations to retrain the classifier, and then we can calibrate the classifier. Next, let's look at these three steps one by one. Firstly, let's look at the feature distribution estimation. For semantics related tasks such as the image classification problem, the features learned by deep neural networks can be approximated with a mixture of Gaussian distribution. Theoretically, any continuous distribution can be approximated by using a finite number of mixture of Gaussian distributions. So in this paper, they have assumption that is the features of each class follow a Gaussian distribution, and it can be represented by a mean and a covariance parameters. And the first step of the feature distribution estimation is the server will send the global feature extractor to all clients. And after receiving the feature extractor, each client will produce the features based on its own data set. In this vector, C is the class index, K is the client index, and G is the data index. So these features can be obtained according to the feature extractor. After having the output features, we can compute the local mean and covariance of the produced features, and we can obtain a local mean and a local covariance for each class in each client. And the fourth step is that each client will upload this local mean and the local covariance to the server. And the last step, the server will aggregate all the local mean and the local covariance and obtain the global mean and the global covariance. And then we can get the estimation of the feature distribution among all data sets of the clients. That's the first step. We call it feature distribution estimation. And the second step is virtual representations generation. After receiving this, after estimated the Gaussian distribution, the servers will generate a set of virtual features from this distribution. And the number of features in each class could be determined by this fraction. And it will be determined by the number of data samples in each class. And the third step is classifier retraining. After generating these virtual representations, we can use these virtual representations to retrain the classifier. And we can easily use the gradient descent methods to do that. Therefore, we can get our final classification model. It includes two parts. One is a pre-trained feature extractor, and the other one is calibrated classifiers by using the virtual representations. In this paper, the authors also mentioned the privacy protection property of their methods. For their method, each client only needs to upload the local Gaussian stochastics rather than the row representations, so it can preserve the privacy of the sensitive information. Let me summarize their algorithms. From the client points of view, each client will produce its own local features based on the feature extractor, and then they compute the mean and the covariance of the produced features, and it will send the mean and the covariance to the server. And from the server side, the server will collect all local means and all local covariance and compute the global mean and the global covariance, and then they can generate the virtual features from this Gaussian distribution. And finally, they will use these virtual features to retrain the classifier and get the final calibrated classification models. So that's their algorithm part. Next, let's move to the performance evaluation part. In their papers, they consider three data sets: CIFAR10, CIFAR100, and CNIC10. The CNIC10 is constructed from both the ImageNet and the CIFAR10 datasets. And they have two models. One is a 4-layer CNN with 2-layer MLP models on CIFAR10 dataset. And for CIFAR100 and CNIC10, they use the MobileNet V2 models. And one trick in their paper is that they apply the ReLU and the two-case transformation before the classifier retraining to make the virtual representations more Gaussian-like. And in their paper, they consider 4 baselines. The first one is a federated average, the typical federated learning method. And the second one is FedProx. In FedProx, we add a regularization term on the local loss function to make the local objective consistent with the global model. And the third one is a federated average M. It adopts the momentum update on the server side. It can mitigate the oscillation for the non-IID training, since the global model only use gradients collected from clients with a limited sub of labels. So the gradients will not be trusted and they will cause the oscillation. And this method will mitigate the oscillation and speed up the convergence. And the fourth method is the Moon. It adopts a contrastive loss to maximize the agreement of the local model and the global model. And the simulation results are shown in this table. Oracle means the whole data set are available for classifier calibration. So for their proposed CCVR methods, they only use a subset of the data to calibrate the classifier. And from these figures, we can find that their proposed CCVR methods consistently improves all baselines. And this is particularly inspiring because CCVR requires no modifications to the original federated learning methods. One can easily get a considerable accuracy profits by simply apply these post-processing methods. And the second observation is the improvement on CIFAR10 dataset is really small. The reason is that there are 100 classes in CIFAR 100 dataset is really small. The reason is that there are 100 classes in CIFAR 100. So the number of images in each class is relatively small. Therefore, the feature quality is poor, and the final performance based on both the biased classifier and the feature quality. And the third observation is improvements on SIGNIC10 dataset is huge. To further analyze the reason of this success and the characteristics of the CCVR, we further show the visualization of the features learned by a federated average on SIGNIC10 dataset. And this is their visualization results of the features learned by the federated average on SIGNIC10. The first figure is the ground truth of the label. And the second one is prediction results before the calibration. And the third figure is prediction results after the calibration. And from the first and second figures, we can observe that some classes dominate the classification results, while certain classes are rarely prediction correctly. For example, the classifier makes wrong predictions for most of the samples in these two circles. And for the ground truth, we can see that the feature colored green and this colored purple can be easily separated. And however, due to the bias in the classifier, nearly all purple features are wrongly classified as the green classes. And observing the third graph, we find that by applying CCVR, these misclassifications are somehow corrected. So we have the observations that there exists a bias in the classifier before the calibration. And we also found that with CCVR, the mistakes are basically made when identifying easily confused features that are close to the decision boundary, rather than a majority of features that belongs to a certain classes. For example, it cannot for the CCVR, it cannot entirely correct the features located in the center line between green classes and purple classes. But for the samples in this circle, the gray samples, they can be entirely corrected, since it is located in the center of the class, not in the boundary of the class. Therefore, we have the conclusion that the CCVR may be effective in models with good feature representations, but serious classifier bias. And that's their conclusion. And next, let's see some other observations found in this paper. The first one is hyperparameters in CCVR. And in their CCVR method, they only have one hyperparameter, that is the number of virtual features for each class to generate. And in general, we can find that even sampling only a few features can significantly increase the classification accuracy. For example, the 200 samples, the 200 features in each class is enough. And the second observation is how does CCVR improve the classifier? To check whether CCVR can eliminate the classifier's bias, they visualize the L2 norm of the classifier weight vectors before and after the applying the CCVR. And we can find that the distributions of the classifier weight L2 norm are imbalanced without CCVR. However, the imbalanceness is obviously reduced after applying the CCVR. It means that the classifiers become fire when making decisions. Considering a large L2 norm often yields a large logic, and thus a higher possibility will be predicted. So CCVR method is able to balance the weights L2 norm to reduce the bias. And finally, let me conclude this paper. For this paper, they first observed that the classifiers of different local models are less similar than other layers, and there exists a bias among the classifiers. And secondly, they propose a novel method called CCVR, which samples the virtual features from an approximated GMM model to calibrate the classifier. And finally, the experimental results show that the proposed CCVR methods improves over several popular federated learning algorithms. And that's all for my presentation. Thanks for your listening. Are there any questions?
Dian, could you go back to the table CCVR and the last one, do the calibration with the data? Yeah, Oracle. So could you elaborate more on Oracle?
Oracle means since we need the data to as shown here. Yes, since we need data to predict, we need data to produce the features, and we need to estimate the distribution of these features. So the Oracle means we use the whole data set to generate the features. And their proposed CCVR means we only use a subset of the data set to generate the features. With more data to generate the feature, the estimation will be more accuracy.
So for the Oracle, they follow the rest of steps as the CCVR, right?
Yes, but yes, only use the whole data set.
Or they follow the same procedure, extract the feature, do the calculation like the mean and the covariance.
Yes. It can be seen as an ideal case of the CCVR, where they use the whole data set.
Okay.
Hello, Dian. Did the author try other methods to generate the non-IID data, except for the Dirichlet distribution?
They only use the Dirichlet distribution. They don't use some other methods to set the non-IID level.
Okay.
Yes.
It seems the paper just like, I augmented the feature, right? So instead of data augmentation, we do the feature augmentation according to a certain kind of distribution, right? Then
yes, something like that. But they mainly focus on calibrate the classifier, not the whole model parameters or the whole feature maps.
Yeah, I agree. But,
Yeah, I cannot understand. So how to generate this virtual feature? You just has one line to show use the Gaussian distribution, but why it can generate a virtual feature?
Since they have the assumption that the features follows a Gaussian distribution. So if we have the mean and covariance, we can generate the samples based on this distribution.
Yeah, but if this is a strong assumption, how can they guarantee that so each class will follow this distribution?
Yes, the authors also say the limitation of their methods. They say that this assumption may be held in image classification problems, but it may not be held in some natural language processing or some other machine learning models. So it is not a very strong assumption, but we still can do that in the image classification problems.
Okay. And also for this calibration, so it is only performed in one round, or like in each round we need to conduct this calibration?
It's a it's a post-processing method, which means we have already trained the model and we calibrate it in several. I think we still need to take several steps to calibrate it.
But why we don't do this in the early stage? I think in the early stage, so like we generate this virtual feature and give them to the client. I think it can better to train this model.
I think the authors think their methods can be considered add-on term on any methods. So they don't want to modify the training process of the original methods. They just want to add these methods in the front of the original method as an add-on term.
I think it's because without federated learning, you don't have the pre-trained feature extractor, right?
I think it's not hard to add on. So just based on the current training, you just add this feature extractor and feed to the model. It's not hard to implement. So so I don't think it will need to modify to like too much things here.
Yes, but they only implement their methods after the training. I don't know why they add it during the training process.
Okay. Okay. Another issue is that so they mentioned that they only need to upload this local Gaussian statistic. But actually,
Yes.
for each client, they also need to send the number of data sample to the server, right?
Yes, we need this NC.
Yeah, this also refers to the privacy issue. And also, I'm thinking, so it's like that the server gives some virtual feature to the client, let the client to train. After that, the client will send the parameter to the server. But if based on this, I think it's possible that for the server to infer the original training set, it should be possible. It's just like, so now the new training, he has the previous training parameter, and now he gave some knowing data to the client, let him to retrain. After retraining, and then so the client sends the new parameter to the server. Based on this parameter, I think it's possible that for the server to infer the client's private data. Yeah, I just guess this. So I think if this is possible, I think this method it will involve serious the security issue.
Yes, but compared to the original methods, they only need to upload extra mean and variance. And I think the privacy level should be consistent with the original federated learning methods, right?
No, it's I think now, so because it's like that before he give the virtual feature, he already have the training parameter.
Yes,
so the next he give the virtual feature and the local client retrain the model and send the new parameter. So based on this, so I think so it's just like you cover it's like in the current inference attack, you have a full training set. You already know half of the data, and also you know all the parameters, and also you know the machine learning algorithm. I think it's supposed, and also that all of them follow the same distribution. I think it's possible to infer another part or mask the training data.
I think these virtual features are generated on the server side, so the client will not obtain these features. So even though these features can contain some sensitive information, yes.
But he still need to send this to the client for retraining, right?
No, the retraining means we only need to retrain the global model. We don't need to retrain the local model.
Okay, I see.
Yes, here, so we only need to, after we have this estimation, we only need to calibrate the global classifier. No client will participate in this stage.
I think if you want to extend this case to personalized further learning, probably what Dr. Yuan said really makes sense, right?
Yeah, yes.
Yeah, okay. If it's just at the server, I think it doesn't matter. Yeah, I misunderstand this part.
Yes, right.
Any other questions? I think they have very interesting observation and which motivates them to develop this approach.
Yeah, I agree. I think the observation is very important. So it's kind of like give some insights.
Yeah, yes.
Okay then. If no further question, let's thank Dian for the good presentation. All right, guys.
Thank you, Dean.
Thank you.
Bye.